Bismillah ar-Rahman ar-Rahim. This is the second video about power and sequence networks. I am going to start from the equations that we obtained in the first video. These equations, the first equation is the apparent power, SP equals to VA, VB, VC transpose multiplied by IA, IB, IC conjugate. And the second equation is V phases equals to A multiplied by V sequences. Okay, this is the first equation and this is the second equation. Also, we obtain the following equation: I of phases equals to the matrix A multiplied by IS. This is the third equation. And also we have the equation of Vs equals to inverse of A multiplied by V phases. And the equation of IS equals to inverse of A multiplied by I phases. This is the equation number 5. So all these equations we have got in the first video. This is the apparent power in phase domain. Phase domain. That means we can calculate the apparent power by means of the phase quantities. These are the phase quantities of voltages, and these are the phase quantities of the currents. Equation number 2 and 3, by means of these equations, we can transform the phase quantities to the sequence quantities. Okay, and by means of the equations number 4 and 5, we can transform the sequence quantities to the phase quantities. Okay, so by means of these equations, the equation number 2, 3, 4, 5, we can transform phase quantities to sequence quantities, or vice versa, the sequence quantities to the phase quantities. Now the equation number 1 can be written as follows: S P, the apparent power is equal to V phases transpose multiplied by I phases conjugate. Number 6. V phase transpose, this is the column vector of VA, VB, VC. And the I phases is the currents IA, IB, IC with the conjugate quantities. We take the conjugate quantities of the currents and we take the transpose of the voltages. Okay. Now, as we see from equation number 2, V phases is equal to A multiplied by Vs. So, and I phases is equal to A multiplied by Is. So, equation number 6 can be written as follows. SP equals to matrix A multiplied by Vs. This is instead, or if we substitute the equation number 2 on the equation number 6, and the transpose of the product of the two matrices, and I phases is equal to the matrix A multiplied by Is conjugate. This is the equation number 7. Okay. Now, if we know from the reversal rule in matrix and the matrices, that if we have A multiplied by Vs transpose, this is equal to A transpose by Vs transpose. Okay, so the transpose of the product of two matrices is equal to the product of the transposes of the is like this. In the reverse order. Is Vs transpose multiplied by A transpose. So the transpose of the product of two matrices is equal to the transposes of the product of the two matrices in reverse order. Okay, and while the conjugate of the product of two matrices can be written as follows. Is equals to here the same order, unlike the product on the transpose case. A conjugate multiplied by is conjugate. Okay, so if we substituting equation number 8 and 9 in equation number 7, we obtained the following equation. S, the apparent power, is equal to Vs transpose multiplied by A transpose multiplied by A conjugate multiplied by is conjugate. This is the equation number 10. Now, as we see from the equation number 10, that we have the multiplication of the matrix A transpose multiplied by A conjugate. We have the following. The multiplication of A transpose by A conjugate is equal to A. We know that A is equal to 1, 1, 1, A square, A, 1, A square. The transpose of this matrix multiplied by A conjugate. A 1, 2, 1, 1, 1, 1, A square, A 1, A square, the conjugate. As we said in the previous video, that the transpose of A is, the transpose of this matrix is as follow. The row becomes column, the second row becomes the second row becomes the second column, the third row becomes the third column. This is the transpose of the matrix A, and the conjugate of each term in this matrix is as follows. The conjugate of 1 is 1, 1, 1, 1, and also we said that the conjugate of A square is A, and the conjugate of A is A square, A square, A. Okay, if we multiply these two matrices, we obtain the following matrix, a matrix 3 by 3, 3 rows by 3 columns, 3, 0, 0, 0, 3, 0, 0, 0, 3. This is the result of the multiplication of A transpose multiplied by A conjugate, and it can be written like this. 3 multiplied by the unity matrix. 0, 0, 0, 1, 0, 0, 0, 1. Okay, this is a equation number 11. If we substituting equation number 11 in equation number 10, we obtain the following equation. Raise. Okay. S transpose this value, and instead of the multiplication of the product of the two matrices A transpose A conjugate, we substitute equation number 11. So we multiply by 3. There the unity matrix. The unity matrix multiplied by IS conjugate. IS conjugate. This is equation number 12. Okay. Now, also we can write equation number 11 as like this. S for the three phases is equal to V naught, V1, V2 by 3 multiplied by I0, I1 conjugate. Equation number 13, and it is the same as the equation number. We see that the sequence voltages of the phase A, the zero sequence voltage, the positive sequence voltage, and the negative sequence voltage. And here we have the zero sequence current and the positive sequence current and the negative sequence current. This equation is equal to 3 V naught I naught conjugate plus 3 V1 I1 conjugate plus 3 V2 I2 conjugate. This is the final equation. This is the final equation that enable us to calculate the apparent power by means of the sequence quantities. As we see from equation number 14, this value is the power of the zero sequence network okay, while this is the positive sequence power, the power of the positive sequence network. This is the power of the negative sequence network. So the summation of the power of the zero sequence power and the positive sequence power, negative sequence power is equal to the three-phase power of the original system. Okay, of the original system. As we see that we can calculate the apparent power of the three-phase system by means the sequence components, by the sequence components of the voltages and by means of the sequence components of the currents. We also can rewrite equation number 14 as follows: S of P, the three-phase apparent power, is equal to S naught plus S1 plus S2. This is the power for the sequence network, the zero sequence network, and this is the power for the positive sequence network, and the third term is the negative sequence network. Let us stop here and see you soon in the third video to solve an example about how we can calculate the apparent power using the sequence components. Goodbye.